Hey guys, this is Elena from Relearn to Share. In this video, we're going to cover this question from chapter 8, rotational motion. So let's read the question. A uniform rod of mass m and length L can pivot freely about a hinge attached to a wall, as in figure 8-63. So the rod is held horizontally and then released. At the moment of release, determine A, the angular acceleration of the rod, and B, the linear acceleration of the tip of the rod. Assume that the force of gravity acts at the center of the mass of the rod from the CM as shown. So let's solve for the first step, A. So we're going to figure out the angular acceleration of the rod. And remember that the force of gravity acts through the center of the mass, or CM, and this will cause a clockwise torque. And therefore, it will produce an angular acceleration. And so at the moment of release, we can assume that the force of gravity is perpendicular to the lever arm from the hinge to the CM. So we're going to use the formula torque equals inertia I times alpha, the angular acceleration. And if we organize this formula by alpha, it will be alpha equals I torque, right? And over here, we should remember that the inertia over here would be the rod about end, which would be the 1/3 m times L square, because normally we would write something like this, right? And the radius over here is L. So this is why we're going to write ml square, which is the I rod about end. And torque would be the torque gravity, so it would be 1/2 mgl, which is the torque gravity. So therefore, if we organize this, it would be like mgl ml square over 3. So if you do this and this, it would be 2ml square, and you will have 3 mgl. You're going to cross out this, and this. So at the end, it would be 3g over 2l. Right, so this would be the angular acceleration of the rod. And now we're going to figure out for the second step, we're going to figure out the linear acceleration of the tip of the rod. And remember that at the end of the rod, there is a tangential acceleration equal to the angular acceleration times the distance from the hinge, right? So at the end of the rod, the tangential acceleration will be equal to the angular acceleration times the distance from the hinge. And there is no radial acceleration because at the moment of release, the speed of the end of the rod is 0, right? So there is no radial acceleration over here. And thus the tangential acceleration is the entire linear acceleration. And therefore, we can write a formula like this. A linear would be equal to a tangential acceleration, which would be, if you substitute this value into this formula, it would be 2L 3g times L, so 3/2g. And note that this is bigger than the free fall acceleration of g. Yeah, so this would be the end of the video, and thanks for watching.